And our topic today is the maritime continent monsoon. And when people think of monsoon, the usual picture that comes into mind is a planetary scale circulation driven by the continent ocean thermal contrast. And this contrast uh, is related to seasonal changes. And the monsoon circulation usually includes the reversal of seasonal wind and also the production of the maxima seasonal rainfall in the annual cycle. Uh, the term monsoon in Chinese words means seasonal wind, but to most people, it is the maxima rainfall season in the annual cycle. And this will also be the definition in this talk. We're interested in maritime continent monsoon for one special reason. That is because the the continent ocean contrast as far as the land area, continent land area is concerned, over the equatorial maritime continent. This really is a huge area of 20,000 islands and peninsula. And so this means that there's a lot of mesoscale terrain features, and these mesoscale terrain features turn out to be very important in the monsoon behavior, in deciding or controlling the monsoon rainfall, such that the planetary scale view, seasonal view, needs to be modified. And there are many remarkable uh, features that arises from the mesoscale interactions with the large-scale winds. And here we're going to address three of them. The first one is the intertwining of boreal summer and winter regimes. And this will lead to a discussion of the asymmetric seasonal transition. And throughout this talk, when we talk about season, we always mean boreal season, means boreal summer and boreal winter. So here is a sort of schematic diagram. It actually is a mean OLR, that's outgoing long wave radiation picture during summer, and such that we can see the maxima rainfall area, or the summer monsoon rainfall, is centered in South Asia. In this particular case, it seems to be in the Bay of Bengal of Indian Ocean. And this would release latent heat and drives the circulation. So we put a red circle to indicate this is the heat source of the summer monsoon. And in winter, this heat source would move to the maritime continent region near or south of the equator. The change is what we call the seasonal transition. If we here is a diagram of following the OLR done by Bill Lau and his associate many years ago, which indicates the maxima convective rainfall represented by OLR is moving from the summer monsoon region in South Asia to the winter monsoon region in maritime continent and northern Australia. The numbers here refers to the months, so 7 would be July. So the convection moves continuously, orderly from July, August, September, October, November, December, January, and February. That is the transition from summer to winter. But in the reverse, in the return path, if this work by Lin He and Bing Wang, the March and April convection are stuck in the equatorial or south of equatorial regions. They do not trace the path of the coming path. They seem to not be able to return to South Asia until May, and of course in June. where you would have the summer monsoon onset. So the return path is an abrupt onset, and that is where the symmetry is. And we're going to show that this asymmetric seasonal march or transition might have something to might be due to the mesoscale complex topography we're talking about. The following will be a number of charts that shows satellite rainfall and sea surface winds. In the old days, the rainfall from trimmed satellite and the sea surface wind from quickscat. DGF would represent the winter season, and here the seasonal winds is mainly northeasterly, that's the northeast monsoon, north of the equator, and the maximum rainfall will be in the equatorial region. It actually spreads between 10 south and 10 north. The summer diagram looks like this. You would have southwest monsoon winds north of the equator. Then you have all this rainfall over all of the north of the equator region, but also south of the equator. If we take the difference between winter and summer, so this chart minus this chart, so we have this result. Firstly, we're going to see northeasterly winds because that's the difference. Winter minus summer, so northeast minus southwest, you get twice of more northeast winds. That's wind difference north of the equator. The color scheme is such that if the summer rainfall, which means winter less than summer, we're going to have the warm color, and if winter has more rainfall, then we're going to have the cold color. Using this chart, we can roughly divide this area into the summer monsoon region and the winter monsoon region, so that north of the equator, it is the summer monsoon region, south of the equator, it is the winter monsoon region. But there is a kind of asymmetry in that the winter monsoon region, which is south of the equator, have fingers that penetrate into the summer monsoon region, but you don't have same kind of summer monsoon region penetrating into the winter. So that's the difference. And therefore, if you focus on north of the equator, which is supposed to be the summer region, you have a lot of this local finger-like winter region there, and that is mostly due to the interaction of the northeast winds and the terrain. So if we look at all those areas and all these regions where northeast winds produce interaction, produce rainfall. So these are the winter monsoon region embedded in the summer region. For instance, over Philippines, the eastern side would belong to winter monsoon region during winter, DGF, but the western side, I should just say the eastern side is the winter monsoon region, the western side of Philippines, the summer monsoon region, because during summer, you have the southwest winds interacting with the terrain. And this is true throughout the area with one exception. That exception occurs over western coast of Borneo. Here you have this north of the equator, so this is the summer monsoon region, but you have some spotty winter monsoon region there. So that means the winter rainfall is maxima. But here, you don't have the winds normal to the coastline, but instead the winds are parallel to the coastline. And why would we have rainfall maxima when you have parallel winds rather than perpendicular winds? That is because you have very weak surface winds over the land and very strong northeast winds over South China Sea. So you create a horizontal shear vorticity that's pretty strong. And that strong shear vorticity coupled with the warm sea surface, a lot of moisture supply all year around, and give you convection here. So you have shear vorticity plus moisture convection, and that would produce what we call a Borneo vortex in this region. That is a frequency distribution, and this is both a seasonal mean feature and a synaptic disturbance feature. Namely, you will see variations or fluctuations of this stationary vortex feature, sometimes stronger, sometimes weaker on a day-to-day basis. That would be a synaptic disturbance. But if you take a seasonal mean, it's there. It's very persistent and prominent due to shear vorticity and moisture. And Borneo vortex actually leads to the development of Typhoon Vamei in 2001. This is the only observed typhoon or tropical cyclone genesis in the equatorial belt. It's a very rare situation that we're going to talk about on the third part of this talk. Now back to the seasonal transition. This is also a difference chart between rainfall of seasons, but it's more complicated than the previous winter minus summer chart. This is the difference between term A and term B, as indicated on the top. Term A is the rainfall of either the fall, that's SON, September, October, November, or spring, March, April, May, minus term B, that is the maxima of the summer or winter rainfall. So the result shows the maxima, either the maximum rainfall occurs in fall, which would be the warm color, or in spring. They have to be higher than both the summer and winter rainfall to be displayed here. And so in a way, this chart will give us the distribution of spring monsoon and fall monsoon. The fall monsoon will be the red color, the spring monsoon will be the green color. So we can see that the fall monsoon region, which means fall gives you the maximum rainfall in the annual cycle, it is like a continuous march from South Asia to Maritime continent. So that's just the interseason, that's the intermediate season. And so this allows convection, or this indicates convection moving in this way, in a continuous orderly. But the spring monsoon area are concentrated in the equatorial region. So in the springtime, we do not have a continuous return path. Everything got stuck in the equatorial region. That's what we're talking about. That's clearly indicated here. By the way, the winds here are not differences. The winds are either fall wind or spring wind. So this chart displays this what we call asymmetric transition. Why the spring monsoon rainfall could not retrace the fall path and going back. So actually, this is also related to the term called spring forecast barrier. Namely, it is difficult to make seasonal rainfall across the spring season. So we're going to show another different chart trying to explain this situation or find the reason for this situation. Here, the difference is in sea level pressure. It's fall minus spring sea level pressure. And where you see a warm color, the red color means a higher sea level pressure. So this chart shows the fall has higher sea level pressure over land, like over Asia continent, and has lower than the over ocean, the sea level pressure is lower. The same is true. It's like this North America, the land has higher pressure, and over North Atlantic Ocean, the sea level pressure is lower. And the reverse is true. Namely, in spring, the ocean would have, the land area would, in fall, the land area would have a lower sea level pressure. The ocean area would have higher ocean sea level pressure. Explanation is quite obvious, simply because of the difference in heat capacity, so that ocean temperature changes always lags behind land, such that when it's fall time, the land surface already cools faster than the ocean, so the land is going to have a higher sea level pressure compared to the ocean. So you're going to have these differences, and the reverse is true in the southern hemisphere. The only exception is in the polar region. So both North Pole and South Pole shows the same color. That means during fall, both North and South Pole region has lower sea level pressure. And the reason is also obvious because North Pole is ocean while the South Polar region is land. So this difference in thermal capacity or in the speed of thermal changes between land and ocean gives us this kind of sea level pressure differences. I'm going to use the term biased sea level pressure. Bias in the way that the fall season has a bias, or the spring season. In the transition season, there's a bias between land and ocean that produces naturally sea level pressure difference between land and ocean regions. We now focus our attention to the maritime continent region indicated by this rectangular. So if we focus on in this our area, expanded, it's going to look like this. Here we have those biased sea level pressure in isobars. So the solid lines means biased sea level pressure is higher over land in fall and in northern land, and in northern ocean, western North Pacific, the sea level pressure, bias sea level pressure is negative, it's lower. If we consider these are isobars, then it's possible to draw geostrophic or near geostrophic winds, or at least a tendency of somewhat geostrophic winds based on the bias isobar. So the bias wind, sea level pressure, bias sea level winds or surface wind could be drawn in this way. This is simply heuristically just follow the isobars. And interestingly, this biased sea level wind is going to give us biased sea level horizontal divergence and convergence, with the most distinct area is over this region. This shaded area would have biased horizontal convergence in fall and biased horizontal divergence in spring. Now we know that during the seasonal march or seasonal transition between summer monsoon near South Asia over South seasonal march to winter monsoon, the equator and south of the equator, this seasonal march is going to follow, or the convection is going to go through this bias convergence region. And when you have bias low-level convergence, it helps the convection. So there's no problem. It's a favorable or friendly area for the seasonal march to occur, seasonal march of convection. But in the spring, when the winter monsoon is trying to return, leave, and to become summer monsoon in South Asia, that convection path has to go through this region of bias divergence in this case. So this is no longer friendly, it's a hostile area. So it will be difficult for convection to move, pass through this barrier region. And that would be our theory of trying to explain why there is this spring barrier, why the seasonal march or seasonal transition is asymmetric. That, of course, is one theory, and there are a lot of many other factors involved here in a lot of research of the spring barrier problem. Just to check if this hypothesis, the argument from this chart, has any merit, Professor Zhou Wang of University of Illinois did a numerical study. Okay, here shows the march on one side and the return the other direction. Here there are three diagrams, or you could say, well, okay, the top diagram is observed, is the data from some data set. I think it's NCEP NCAR analysis. And that shows the difference between fall and spring sea surface temperature. I'm sorry, that doesn't look like it. Oh, surface temperature. It's not only surface temperature. And the middle chart is a control run, and the bottom chart is the experimental run. The control run would use the sea surface temperature data that the difference between fall and spring that include or implies necessarily the seasonal asymmetric sea surface temperatures. The bottom chart will remove these asymmetries, which is average the fall and spring sea surface temperatures. So you have very little variation in sea surface temperature. And we can skip this one. No, we can't. Here shows, I guess we can, I forgot the details. Anyhow, so the control runs and the experimental symmetric run are using GCM models. And the result shows in this time series, time and latitude series of the, I think that annual variation precipitation of rainfall. So if we look at the data set, the rainfall variation has a break, a minimum from winter to summer. It also shows the same, a minimum or a break in this control run. But in the symmetric run, where we try to remove a symmetry, then this break is smaller. There seems to be a bit more continuous than the control run or than what's indicated in the data. So this is the modeling effort published in 2008 showing that the seasonal biased temperature or thermal patterns that related to seasonal bias, the sea level pressure pattern and winds do have an effect that seem to explain at least part of the asymmetric seasonal transition. And this, of course, is due to the geography of the maritime continent area, the terrain. The next aspect about this terrain distribution is the loss of seasonal predictability during ENSO. We know that the reason we are able to make seasonal forecast or seasonal prediction is largely because of ENSO, which of course changes SST and circulation patterns. If there were no ENSO, or if we could not predict ENSO, then it would be a lot harder to make seasonal forecasts in most places globally. This is UC Berkeley on their website shows that what ENSO does to the rainfall distribution, and then they have all these heavy rainfall islands, Pacific during ENSO, during El Nino, what drought in Australia, warmer than normal, northern U.S. and so forth. Then there's the impact in California. Actually, this was totally wrong in the last El Nino we had. I think it was 2022, or 2023. Regardless, that's the predictability source, and so it's plays an important role. And in such that there's a concept, kind of a conception that El Nino has more influence or stronger influence over the maritime continent if you look at many of the work or map or studies. During such that if there's El Nino, then the convection moves to the east along the equator. So there tend to be drought over the maritime continent. One example is in the 2015-2016 El Nino, where the forest fire became very severe, uh, and it impact on commercial air flights. A lot of commercial flights were canceled, and this is all over the world newspaper headlines of this Indonesian forest fires. Forest fires not only because of ENSO or El Nino. Farmers would try to uh, start fires for agricultural reasons every winter. But this strong El Nino season 2015-16 in particular caused a lot of damage and impact lasting for months or longer. Based on this, we would tend to think during El Nino, it's easy to forecast. For El Nino, you're going to have drought over the maritime continent, especially the western side. And La Nina, you're going to have flood. This turned out to be not the case. Starting in 2013, the ASEAN countries, Association of Southeast Asian Nations, begins a climate outlook forum. This is the WMO program that's taking place in several regions of the world. And for this Southeast Asia region, the ASEAN COF Climate Outlook Forum started in the winter of 2013-14. Here is the forecast in that first winter season. From all this, every country in Asia sent a forecaster to a place. In this year, it was Singapore. And they sit together, review the global NWP Center forecast, like the European Center, UK Met, JMA, CMA, I think there's APCC. And then they agreed on a consensus forecast. They would divide the area into several regions or sectors, and each sector they were going to call for the probability of rainfall being normal, above normal, normal, or below normal. We focus on this Western Maritime continent region. I think this one probably is not on 2030, but just an example. In this one, it shows 30, 40, 30, which means the consensus is that there's more likely to be normal than either above or below normal. We look at all these this Asian COF results over several, let's say that's 2013, 14 through 2021, 22. The number is 1357 because COF operates twice a year, and the even numbers are for summer and the odd number for winter. If you look through here, with the exception of 2018-19, every year the largest probability is in the normal or near normal region. The first year is still 35, 35, 30. Actually, it was 30, 40, 30. But one of the countries' representatives said at the meeting that we already released our winter forecast and we call for above normal for this region. So the group decided, well, we should not embarrass that country, so let's compromise. So we call it 35, 35, 30. But reality was 40, 50, 40, 40, 40, 50, 40, 40 with one exception. If you do the verification, there was no data to verify these 3 years. Then every year was wrong, including the season where the forecaster has the courage or where the models do agree and they call for above normal, it was wrong. It was normal that year. The reason this was the case is because the models do not normally agree with each other. So this is an area of low confidence, low predictability. So that is quite in contrast with the conception that El Nino or ENSO gives a high predictability for this area. So we're trying to understand why this is the case. There were some previous studies showing that sea surface temperature in the Eastern Pacific, versus the rainfall over this area has minimal correlations. Usually, the correlation pattern has a horseshoe pattern, but in this earlier work, we show there's a minimal correlation, means the correlation, the prediction based on this relationship is going to have problem in this area. More recent work, either overlap or longer period, all shows this particular area has low correlations. So we need a reason for this no correlation. So here we revisit the ASEAN COF, but using better data, more clear defined satellite data and map and region. And there's a chart. I won't go through all these, but simply saying, if you look at whether that particular system's El Nino or La Nina or neutral, the horseshoe pattern usually are in agreement with our previous concept. El Nino tend to be dry and La Nina tend to be wet. But when you look at that particular area, which is the Western Maritime continent, we would focus on Sumatra Island, the South Malay Peninsula, and West Borneo. Okay, Sumatra Island, South Malay Peninsula, and Borneo, Western Borneo. Then there are a lot more misses than hits. Try to explain this. We're going to show that there's a reason for this. ENSO has this typical or schematic model of change of water circulation. So during El Nino, you would have convection over Eastern Pacific, Littoral Pacific. While during La Nina, it shifts to the west. Okay, so the horizontal map shows that during El Nino, you're going to have this horseshoe pattern of wet anomaly, but we should have drought over Western Maritime continent or over Maritime continent. El Nino is the opposite. We have the horseshoe pattern of drought, but when more convection, so Maritime continent should be wet. That's one effect of ENSO on water circulation. But there's another effect that Bin Wang and his associates since the early 2000s have shown that there's this Philippine anticyclones or during winter, during ENSO phase, El Nino phase, such that you have horizontal winds, anticyclonic winds, and that goes into the South China Sea. And this chart, the left charts are the East Pacific El Nino and La Nina situation, and then you have Central Pacific El Nino, La Nina situation. They are similar, so we don't have to differentiate here. We're just saying ENSO or has two effects. One is the water circulation being shift east-west. The other one is this Philippine anticyclone or cyclonic circulation. It's more than just Philippines, covers a large area into the South China Sea, even Indian Ocean. If you put the two together, then we have this schematic diagram. So El Nino, you have the Philippine anticyclone. La Nina, you have the cyclone. But you have the worker circulation. The worker circulation equatorial zonal winds are consistent with the Philippine cyclone anticyclone. If we look at the left chart, here is the La Nina situation. We're supposed to have a wet phase. El Nino is supposed to have a dry phase. But in this wet phase of ENSO, La Nina, you have westerlies along the equator. The westerlies from Indian Ocean would hit the western coast of Sumatra. There are narrow mountain range. So the mesoscale terrain would create heavy rainfall to its west due to the wind-terrain interaction. So the wind that's going over here still west into the South China, it will be drier. So there will be dry here. So I put down here wet phase, but dry in the South China, in this region. For El Nino, this is supposed to be a dry phase, supposed to be drought in the Indonesian forest fire and the smoke and all that. But the easterlies of this Philippine anticyclone would create rainfall on the east side or in the western part of South China Sea because of the Malay Mountain and also Sumatra Mountains. So this will be a dry phase but wet. So that is why it is difficult to make prediction. That's all due to the mesoscale terrain here. I call that area Western Indonesia Malay Peninsula, short for WIM. That has the English meaning of no confidence, difficult to forecast. Even the best model, if it does not include or represent adequately those mesoscale mountains over Sumatra Malay Peninsula, you're going to have trouble here. The current models mostly do their prediction based on SST. It doesn't matter how good your SST data is or how good your model handles the effect of SST in its mechanisms. The models are going to have huge problems to predict rainfall over this wind region. So that is the second feature of mesoscale terrain that we want to address. Now we come to the last feature, this Typhoon Vamei, which was generated near the equator, very close to equators, equatorial tropical cyclone genesis. If we go to some standard textbooks like this one produced by NCAR, Introduction to Tropical Meteorology, and there's a standard diagram that most people are very, very familiar with. I think showing that there's tropical cyclone occurs north and south of 5 degrees, but there's absence in the equatorial region between north and south. Professor Bill Gray, much earlier in 1968, has give 6 conditions for tropical cyclone development or tropical cyclone genesis, like the SST has to be greater than 26 degrees C, enhanced mid-tropospheric humidity, conditional instability, enhanced low-level relative verticity, weak vertical shear. And the last one says displacement at least 5 latitude away from the equator. And the authors of this textbook then wrote, in recent years, a number of tropical cyclones have remained within 5-degree latitude of the equator. They quote our observation study of Typhoon Vamei, so suggesting a need to relax this constraint. Our paper was published in 2003. But this is wrong. Where is it wrong? We're going to claim that there's not a number of tropical cyclones generated within 5 degrees of latitude. There was only one. And there's a reason for that. Here we use the JAMA, the Japan Meteorological Administration data, all of their TC data, historical data that sees some kind of TC or its pre-existing disturbances in the equatorial region, which is defined to be within 5 degrees. The red latitude lines are 3 degrees. We have both the Pacific, Equatorial Pacific and Equatorial Indian Ocean here. The color code shows disturbances, tropical depression, and tropical storm. Tropical storm have this typhoon symbol that will correspond to weak typhoons in some other definitions. Even though we see quite a number of them during this entire history, or the history starts in 1980, when you have to have satellite first. So the satellite, we didn't have satellite prior to 1980. So this here we're looking at all the TC in the JMA database since the satellite era started, since 1980. Only one system, that's Typhoon Vamei, near Christmas or just before actually Christmas time in 2001, where you see the green color within the 3-degree belt. It actually occurred at 1.5 degrees. So there was only one, not a number of them. And this one is different. It's more than just only one, but the mechanism of the tropical cyclone genesis is different from all the others. In physics, especially now, there are a lot of theoretical work showing various kind of theories, how the universe started, cosmology and very fancy, interesting theories like multiverse, string theory, inflation, and all that. But they all need observation, verification. As of now, we don't have any observation verification, or there might be some people say there's no way you can get observation to verify multiverse or string theory or many world theory or inflation or a cyclic universe and all that. In meteorology, it's the opposite. We almost never had a theory to the hypothesis to predict something is going to happen, and then somebody observe it. Interestingly, this is a rare case where the theory in meteorology precedes the observation. 20 years prior to Typhoon Vamei, very smart guy, this Typhoon Vamei, with a center near Singapore, is Professor Hawk Lim, or in Chinese name, Lin Hao. Professor Lim did a theoretical work, a very simple. I jump ahead too fast. I should first show that Typhoon Vamei occurs prior to Christmas due to the spinning up of vorticity. Here we have surface winds on the top row and the vorticity in the bottom row, and spinning up over where the Borneo vortex usually is. And that's the cyclogenesis. And Professor Lin, he used the simplest possible model, a linear shallow water model on an equatorial beta plane. There's no mean flow, no topography, no moisture, no diabatic heating. It's just a barotropic model, shallow water model. And since we know there's the tropical convection, even 20 years prior to Typhoon Vamei, a lot of weather in the equatorial regions due to the cold surges from the Asian continent, like the outbreak of Siberian high over Mongolia and then moving southeastward and cause a sudden rise in surface pressure over in southern China, and that is a couple of days later you can predict rainfall over Singapore, Malaysia, or Indonesia. So he put a forcing in this shallow water model on the equatorial plane. Okay, that's a key word. So not F plane, but beta Y plane. And he put forcing forcing profiles A, B, and C, just with a different uh, amplitude and speed of variation. So this would indicate at 30-degree north, there's a higher uh, pressure increases or higher pressure, surface pressure that simulates cold surge, and then see what happens after this pressure surge. It is not a numerical model, it's a purely a linear mathematical model, so he can get linear solutions. And here are the solutions that day 3, day 4, day 6, day 9, after the rise of this specified high pressure at 30 north. And this will be the wind patterns. And what we see here would be a geostrophic adjustment, because you put a high pressure there, but wind has to respond to it. So you basically look at a geostrophic adjustment problem. And so you're going to generate linear solutions, which would mean Rossby waves, Kelvin waves, and mixed inertial gravity waves. The time evolution looks like this. And it is interesting that we see a northeast-southwest orientation. And the northeast winds, equator side of the pressure surge, also oriented northeast, southwest, and these are strengthening of northeast winds, very kind of in the same sense as observed the northeast monsoon surges. And to the southeast of it, we have return flow that resemble some sort of a Borneo vortex, if we consider that's the longitude of Borneo. Why is this interesting? Because there's no topography. There's absolutely no topography. There's no continental ocean, and there's no mean flow. But where does the northeast, southwest surge-like pattern come from? And if you remember that for Rossby waves, the speed, well, waves phase speed is fastest for the longest waves. So here we have a wave mode, Rossby wave mode. That's the main part of this. These are equatorial Rossby waves. So longest waves and shortest wave, or the wave scale could be, spatial scale could be defined or recognized as that of the equatorial wave mode. So like n equal to 1, n equal to 2, up to n equal to n. And those number of n's, the lower n's means longer waves, which means there's its maximum amplitude is closer to the equator, and the higher n's, like n equal to 3, would have its maximum amplitude further away from equator compared to n equal to 1. And since the long waves, that's n equal to 1, would move faster than n equal to 2 and n equal to 3, and there's no mean flow, so Rossby wave move westward. So we see that the larger those waves, that means low M modes, would move faster towards west when their maximum amplitude is closer to the equator. So the equatorial features would move westward faster than the features that are away from the equator. That is the reason of this northeast-southwest tilt. So entirely a dynamical reason of Rossby dispersive relationship, not a geography. If we pick just day 3 and day 6, and day 3 and day 6, that's a development, and we see the return for cross equatorial return flow. That's almost like Borneo vortex. You compare this chart with the actual observations of December 19th, December 22nd, prior to the Vamei development, they look quite similar. So I think this is the first time, as far as I know, a theory precedes observation in meteorology. In this case, 20 years earlier. I have to admit one thing there, I kind of cheated a little bit here because the horizontal scale of the theory models and the observations are not the same. The theory chart actually have horizontal scale twice as wide as the observed wind patterns. But we have to understand that there's no mean flow and there's no topography. And there's no South China Sea or Borneo land or Malay Peninsula. If you put land and ocean in there, because the geography, South China Sea is very restricted in the east-west region, and so that restricts moisture in the winds, and that concentrate northeast winds channels through the South China Sea, which gets narrower and narrower towards the equator. One can imagine topography should have an effect that will narrow the horizontal scale of the theoretical solutions. So in a more complete model, we may expect that the dynamical reasons or explanation could still work and be similar to observations. We are going to say why this didn't happen before. Because northeast winds, cold surges occurs every winter. That's why the weather services in Malay and Singapore, Indonesia use cold surges as their forecast of rainfall weather. Borneo vortex is always there every season. We just said that earlier. Why only in 2001 there's this tropical cyclone genus, but not other years? And we haven't observed that again since then. Our explanation is again related to this mesoscale terrain. If you have strong northeasterly surges coming down South China Sea, whatever Borneo vortex you have here is likely to be pushed towards land, right? You can't put a vortex in the middle of South China Sea and have north winds going through it. That's not possible. So if you have northeast winds going through South China Sea, your maximum shear vorticity has to be to the southeast, so your vortex has to be moved towards the land. If you have a vortex that's pushed to the land, even though it's strengthening, spinning up by the northeast winds, half of it is over land, you can't have typhoons. So here we have an interesting situation where the dynamics of the monsoon wind surges and high moisture is favorable for tropical cyclone development, but that developing storm will be close to push towards land so that it will not develop. This is why it is very difficult to develop, even though the theory says so, but the terrain plays two roles. It helps, it concentrates strength in the northeast wind and gives you shear, but it hurts because it prevents the tropical cyclone development. And with some heuristic argument of past data, we presented a kind of an explanation that with some counting fingers, we figured the chance of a Borneo vortex becoming a tropical cyclone is like once every 100 years. The most interesting thing was when this manuscript was in review, John McBride from the Australian Weather Bureau wrote something in the monsoon email discussion, says, that was like the next year. So, we see another Vamei is developing because of the cold surge and Borneo vortex. Then we got nervous, and our paper was just saying that once every 100 years. Now the paper was under review, and John McBride said, another one is developing. But of course, our paper got accepted. Another one has not developed and hasn't been observed ever since. After this Typhoon Vamei, there were several efforts trying to simulate it using regional models, and all the efforts were successful. There are at least 7 papers. They all look at the different mechanisms. Some say the large-scale flow is important. Some say latent heat. Some say boundary layer. And one even say we still need some F. But, well, none of these explanations is what we talk about. We're talking about dispersive relationship of Rossby waves under geostrophic adjustment forcing from pressure surges. These different regional model efforts also have a problem. I'm betting that if these investigators using their models, which they all tune the models, make sure the cyclone develop under the reasonable range of possibilities. If they use the models on a different year, since there will be cold surges every year, there will be moisture, there will be boiling water, they're likely to produce tropical cyclone, not necessarily every winter, but a lot of winters. So that is the problem. The problem is not how Typhoon Vamei develop per se. The real problem is why Typhoon Vamei only developed in 2001 and not in any other years. So the model's focus or goal was wrong. They do not answer the real question. To conclude my talk, I'll use a Chinese poem. I'll translate it into English. It says that this powerful, all-capable model did a lot of work in vain. Here it's the horizontal component of Coriolis parameter is very small. Cyclones cannot develop. Cold surges always cause warm rainfall, such that the equator, even over the equator, strong storms can develop. However, the model goals lost the right focus. So they spent a lot of effort and didn't really do anything real. Because monsoon penetrating into the tropics happens all times, all season. Why is only Vamei developed? The English translation is here. Mighty models prowess turns to waste. The Coriolis coefficient fades away. Cyclones lose heroic sway. Yet cold surges keep hastening warm rains. Even at the equator can a storm twist. Purposes blurred, focus led astray. Mighty models prowess turns to waste. Monsoon winds penetrate deep as always. Why was it only Typhoon Vamei? Thank you.